Hello, everyone. Hello, everyone. Hi. Hey. How you doing, y'all? I'm in Texas. I get to say y'all. So, today's presentation is going to be RouterOS version 7 and its features. Just kidding. It's actually going to be on traffic shaping and bandwidth control. But if you haven't seen the video on the RouterOS version 7 leak, go to the Brothers Wisp Facebook page and you'll see a little leak of some of the candy that offers. So, well, before we go any further, for those of you who don't know me, I am David Attias, and I am a MikroTik certified trainer, and I'm a team member and sponsor of the Brothers Wisp. I own Tone LLC. It's a cloud-hosted VoIP and phone systems provider. And today, we're going to talk about traffic control with HTB. So, before we go any further, who is this presentation for, really? Well, it's really for anybody, but I guess ISPs, MSPs, consultants, network engineers, those are the people that would like to take a look at this. I'm a VoIP guy, so traffic control is incredibly important for me, or for anybody offering VoIP. The suggested skill level for this presentation is going to be beginner and intermediate. I designed this presentation to be understandable. I'm not looking to overwhelm anybody with giant acronyms and trying to impress you. I want people to understand exactly what I'm saying. And the prerequisite is you should have network engineering experience, and you need to have some MikroTik RouterOS experience. And the examples that you're going to see in this presentation are really focused on customer networks, all right? But the principles can really apply anywhere. But the examples are customer networks. And customer networks, by the way, have a capped amount of bandwidth. Just keep that in mind when you're looking at this. So the topics in this presentation are going to be traffic control, obviously. We're going to talk about what is traffic control in QoS. We're going to talk about classifying with Mangle. We're going to talk about scheduling traffic. That involves queues and queue types. We're going to talk about policing versus scheduling. And we're going to do traffic. We're going to talk about shaping traffic with HTB. Namely, what is HTB? Everybody talks about QoS is based on HTB, but I've never actually heard anybody accurately, simply explain what is HTB. We just know it's based on HTB. So we're going to be talking about tokens, buckets, bursting, and then we're going to do a fun lab, actually showing you a live burst of traffic, and we're going to do 2 bursts. So how did that happen? Oh, so what is traffic control? Well, in a nutshell, it's a system that regulates data flows, all right, tries to at least. It ensures sufficient throughput of high priority traffic. It promotes low latency for higher priority traffic. It doesn't create low latency, it promotes it. So how does all this happen? What is like the real blood and guts in a nutshell? What are we doing with traffic control? Well, we're selectively deciding which packets to delay, which packets to drop, and which packets are gonna, which queues are gonna have priority to send out first, second, third. And that's really it in a nutshell. What are we dropping and what are we delaying? So a couple of important points that I should talk about prior to getting into the meat of this topic is, first, the MikroTik has no idea how much your internet bandwidth is, or how much bandwidth you have for that matter. So we need to tell the MikroTik what the total available upload and download bandwidth for the link that we're going to be traffic shaping on. That could be the link that goes out to the internet. That could be the link that faces the local network. The examples I'm going to show you here are the ones facing the local network. I had reasons for that I'll explain later. We can only effectively queue traffic that exits an interface. Just keep that in mind. We have no control over what comes to us, so we can only effectively queue traffic that leaves an interface. Traffic control becomes effective when all available bandwidth of a link is maxed out. Nothing noticeable will happen until you completely flood your uplink. And the simplest, crudest way to overcome traffic congestion problems is to buy more bandwidth. If you're having congestion problems, try getting more bandwidth. If you can't get more bandwidth, then obviously you better learn this stuff. Last point, very important. You could do everything right with queues and traffic shaping and all that, but if your fast track is turned on, none of that will work because fast track bypasses queues. So let's talk about the 3 phases of traffic control. First one is classify. That's going to be marking packets. We need to categorize the traffic. Second is going to be schedule, which involves putting traffic and packets into queues. And the third one is shape traffic, which has to do with dequeuing, when packets are allowed to exit a queue. None of this stuff happens automatically. There are systems, HTB, which I'll explain in detail later, that decides when a packet can leave a queue. So first part is let's classify with Mangle. If any of you follow me on the Brothers Wisp or on my Facebook page, you'll know I'm a big Star Trek fan. Which Star Trek character can really do some mangling? And by the way, Next Generation only. It's the only one I like. Worf of Mog. So he can mangle. He'll mangle your face. So let's talk about classifying traffic with Mangle. Classifying is categorizing traffic. And Mangle is a RouterOS facility that marks packets for future processing. RouterOS only allows 1 packet mark, 1 connection mark, and 1 router mark per packet. We're going to talk about the first 2. The Mangle facility is also used to modify some fields in the IP header, like DSCP and TTL. And Mangle rules are processed sequentially, so be careful the way you set up your Mangle rules, especially if you're going to use the pass-through option for DSCP. If you're doing DSCP, you should have it pass through, because I'm guessing you want to mangle that traffic later on, not just change something in its header. You want to queue it. And it's a good practice to mark the connection first, then use that connection mark to perform a packet mark, if it's possible. And this promotes low CPU usage. So to mark packets, pretty simple. Just go to IP Firewall Mangle on the General tab. You actually click New on the General tab. Pick a chain. I use pre-route. We're going to be marking HTTP traffic, so the protocol is 6, TCP. Our destination ports are 80 and 443. The action is mark connection, and then you give it a name. I just called it http.con. Then you'll see it over here in your Mangle list. We have one there. It's a connection mark, and there's the info for that. And to see that this is actually working and that your connection marks are working, you just go to IP Firewall Connections, and you'll see your connection marks show up here. But unfortunately, when it comes to queuing, you can't really do anything with a connection mark. Queues will only want to know about packet marks, and we'll get to that later. But now you need to mark the packet with a packet mark. So again, the chain I like to use is pre-routing for this. My connection mark, I'm going to use that connection mark that we just created, HTTP-con. That's our classifier. And then the action is going to be mark the packet, and I just give it the name HTTP. Here's what it looks like in the list. You have your connection mark, and then you have your packet mark. And that, again, promotes low CPU usage. And here's just my list of Mangle rules that I like to use. I like to prioritize, TCP acknowledgements, HTTP packets, SIP traffic, RTP traffic, and really anything else you think that's important. So just keep that in mind. Now, scheduling with queues. Which Star Trek person will be doing something with queues? That's right. Who said that? You get $1. So that's pretty good, queue. And a queue is a facility in RouterOS that processes packets prior to exiting a physical interface. It's somewhat of a buffer. A queue is a temporary buffer that packets enter. A queue will either drop, delay, or allow packets to pass unrestricted. Packets that enter a queue may be organized or reorganized based on a chosen algorithm, and MikroTik currently has 4. And this will dictate how the packet, in what order the packet will leave a queue. Queues must be configured with bandwidth limits, and that's very important. No limits, nothing happens. Whoops. And RouterOS queuing implementation is based on HTB. I know I knocked people for saying that before, but I'm actually going to explain to you exactly what that means. That'll be at the end. So now, before we get into what queues are doing and what's happening inside a queue and queue algorithms and all these things, let's just talk about the 2 differences between simple queues and queue trees, because you see both of them, and you're not sure which one to use. They both appear to do the same thing, but there are some pretty amazing differences. So simple queues on one hand, the rules are processed sequentially, all right? And that's important because if you have 100 rules and traffic has to make it all the way to rule 100, that means it had to go through 99 rules to get there. So obviously CPU is a factor there. Simple rules use multiple cores. And simple queues can shape based on the sum total of upload or download traffic. Can be used simple queues can be used with time conditions for when a queue is in effect, and simple queues can also be generated with PPPoE clients. Now none of this over here can happen with queue trees. Now queue trees, on the other hand, all rules are processed at once, and that's because it's single-threaded. And it's only configurable with packet marks, all right? But that's okay, because Mangle has dozens of matchers. But you could also use packet marks in simple queues. So you decide which one is right for you. It's really going to depend on how many rules you have, how much processing power you have, how much bandwidth you're pushing. But these are the pretty major differences between the two. I just tend to use simple queue trees. And in the examples in this presentation are going to be simple queues, because simple queues have a bandwidth graph. Queue trees doesn't. Don't know why. So let's talk about queue sizes and limits. Every queue can have a size and needs to have its limit specified. So queue size is just basically how many packets a queue can hold during congestion. And over here, we see the queue size for the default queue type is 50. Now, limit at is the committed information rate. That is the guaranteed bandwidth for the queue. And the maximum limit is the MIR, maximal information rate. It's the maximum bandwidth that the queue can pass. And queues will only work if queues will not work if max limit is not specified, so please specify them. Now, why is max limit so important? Probably the most important setting in a queue. Why? Because once traffic exceeds the max limit of a queue can be configured to either drop or buffer the packet. And that's when it decides, are we going to buffer this packet? Have we exceeded the max limit? If we have, yes, start buffering packets. If not, packet goes through. That's only if you exceed max limit. Even if you're at the max limit, it won't do it. Only once you start exceeding. And over here, we see a queue buffer size of 8. So we see there's probably congestion. We exceeded the max limit, so we have 3 packets queued over here. That also means more packets can enter. But what happens once the queue is full? Once the queue is full, once the queue size is reached, in other words, packets trying to enter the queue will be dropped. This is known as tail drop. And over here, you see queue is full, packet tries to come in, it gets dropped. Pretty simple. So now it's important to start talking about policing versus scheduling. So what are the differences? What do they do? Well, a policer is, once max limit has exceeded, packets trying to enter this queue are dropped. That's what a policer does. So you see over here in this bandwidth graph, let's say we don't have a policer and traffic is just going where it needs to go. All of a sudden we implement the policer, and at a hard limit, it drops everything that exceeds the police max limit, I guess. None of this traffic is queued. It gets dropped immediately. Scheduling, on the other hand, scheduling is when packets that exceed the max limit are in-queued, and when bandwidth becomes available, packets will dequeue. So over here, same graph as the top. Let's say we implement a queue that once we pass the max limit, if the queue size is big enough, it'll start to queue the packet, and then over time, once bandwidth frees up, it'll release those packets onto the wire. Now, there are a couple of differences about this, but I'll explain that in a second. To configure a queue to police, set the FIFO queue size to 1. So only really 1 packet can go in there. Anything after that, it gets dropped. To configure a queue to schedule, set the FIFO queue size to anything above 1. Again, the default size for the FIFO queue in MikroTik, which is the default queue type, is going to be 50. So here are the differences between policing and scheduling. So policing, again, drops packets that exceed the max limit. It promotes lower latency for packets that are passed, because it's not going to hold any of them. It's just going to let it go. The success rate is really based on priority, so give it a high priority. For example, VoIP, RTP, gets high priority. All right, because we don't want to drop that, and we don't want to queue that. We need that to get out as fast as possible. And this definitely will require better planning to configure effectively. Or should I say for it to be effective? Because, well, if you don't know your network and you don't know what throughput is going through this queue, and you're dropping packets, let's say RTP, that's very bad. You don't want to do that. On the other hand, if you're not sure if you want to use a policer or not, chances are you won't go wrong with a scheduler. At worst case, it'll just delay the packet a little bit. So a scheduler queues packets once the max limit has exceeded. Again, this is when we exceed limits. It creates delay and adds overall latency to the connection. It also has a higher probability of packet delivery because we're not dropping packets. We're just holding them until bandwidth becomes available, until traffic drops below the max limit, then those packets are sent out on the wire. And to configure effectively, if you want this to work no matter what, I'm going to tell you the rules of parent-child size limits. So we're going to talk about child limits rules and the size of the queues. We'll get to that later, and that's really important. It's actually really easy to set up too. So now let's talk about a couple of queue types. Again, MikroTik has 4. First one's going to be FIFO. Just stands for first in, first out. The same sequence in which packets are in-queued, they are de-queued. Packet 1 goes into the queue. Packet 1 exits the queue first, in the same order that it enters. Pretty simple. Here's the logic, and I think now's a good time to probably talk about the nomenclature with queuing. So when we enqueue a packet has entered a queue. When we dequeue a packet has left the queue. So over here, packet for a FIFO queue, packet comes in. First thing the queue does is check to see, are we over the queue size limit? If we are less than the queue size limit, the packet is enqueued and then eventually sent out. If we're over the limit, drop the packet immediately. That pretty much applies to every queue, every queue type. Next one is SFQ, Stochastic Fairness Queuing. Stochastic Fairness Queuing is a hashing algorithm that will classify traffic based on 4 identifiers, then put into any one of 1,024 possible substreams. Dequeuing from substreams will happen in a round-robin fashion. I don't use this, but this basically just means that it's trying to equalize traffic. The problem is, let's say you have 2 users on a LAN. One user opens 1,000 sessions. Another user opens 10 sessions. The user with 1,000 sessions is going to get 100 times more chances to send out traffic than the user with 10 sessions. This can be used if you're sending all traffic to a single host or from a single host, but I just don't use this because it has a serious flaw, which I just explained. And the logic for this is it goes in, hashing algorithm separates it into its subqueues, and then a round-robin fashion, it dequeues. But PCQ, on the other hand, was designed to address the unfairness with SFQ by the use of additional flow identifiers. The flow identifiers can be source address, destination address, source port or destination port. So this is kind of nice because, well, speed limitations can be applied or divided equally by the number of flows, but you can also classify it based on source address. So if you say any single host on, let's say, your LAN, if he's trying to hog all the bandwidth, he won't be able to because he gets his own lane. Whereas in SFQ, he can get all the lanes. So this is good. I use this for large networks that have a lot of HTTP traffic, which usually just ends up happening. And then if you configure this correctly, this will divide the number of subdivisions based on how many sessions based on source IP address or destination IP address. I use the source. And this way, one user cannot take all the bandwidth. So this is nice. And again, we have our logic. We group it by classifier. It goes into its subqueue, and then it'll be dequeued as needed once traffic is available. Red is an interesting one. I kind of like this one. So red is random early detection. It's a queuing mechanism which tries to avoid network congestion by managing the average queue size. What this is really doing is it's trying to prevent TCP windows from collapsing and resetting back to TCP slow start mode, otherwise known as TCP global synchronization. This is pretty cool because it has two different thresholds. If packets coming in here are below the minimum threshold, packet is in queue to get sent out. if a packet is between the minimum threshold and the maximum threshold, the probability of packet drops, which happen randomly, will increase as the queue size increases or the queue gets more full. Again, this is designed to help prevent TCP global synchronization, which is when all the windows collapse down to their slow start mode, which is the smallest TCP window size. So do that with like traffic superfluous traffic, just traffic that you can afford to drop. I do it with the no mark. I put all my no mark traffic into a red. So now let's talk about shaping with HTB. I like to call this the MikroTik Sasquatch, because prior to version 6.35, you didn't see any mention of the word hierarchical, you didn't see any mention of the word token, and you didn't see any mention of the word bucket. Now, since 6.35, now you have an option in the queues called bucket. So it's like we got a glimpse of HTB, like physically seeing one of the words in there. So that's why I call it Sasquatch. You see a quick glimpse and then it disappears. So I like to think of MikroTik HTB as the Sasquatch. And we're going to use Picard to help us because he's the one that says what goes and what doesn't. So shaping with HTB. By the way, I won't kill you to laugh at some bad jokes. So shaping, what is shaping? Shaping is the act of when to allow a packet to exit a queue or to dequeue. Hierarchical token bucket. It builds relationships between queues, and that relationship is going to be parents and children and priorities. Queues can either be parents or children. In Linux terms, they call this inner queues and leaf queues. And I'll talk about the differences. Setting flow limits and priorities is what determines when a packet can be dequeued. And each queue has a bucket size that holds tokens that will be used to escort a packet to its exit interface. So now is a good time to talk about tokens. So what are tokens? We hear about them. What exactly do they do? Well, really their only function is to escort a packet out of a queue. So a packet cannot dequeue without being escorted by a token. One token can dequeue up to 1 kilobyte of traffic. The root parent queue is where token generation happens, and tokens are issued at root parent's max limit rate. Now let's take a look at the hierarchy. So HTB, let's talk about the hierarchical part of HTB. The hierarchy is queues are configured in a hierarchy. Parent and child queues establish a give and take relationship for distributing and consuming bandwidth based on priority. The hierarchy works in one direction and is implemented on an outbound interface. Again, we can only queue traffic that exits an interface. Over here, we see what the hierarchy is. We see our child queues here, which are sub-queues of the parent queue. Now let's talk about parent and child queues. And in Star Trek, we have parents and children, right? Some of the famous ones are Beverly Crusher and Wesley. Don't forget about Worf and his illegitimate son, Alexander Bozhenko. Don't forget about Dr. Noonien Soong, all right, the inventor or creator of data, and Laxwana Troy and Deanna Troy. Did you know that Laxwana married Gene Roddenberry? And she's the voice for the Starship Enterprise computer. So anyway, a little bit of Trek trivia. So parent queues, what are parent queues really responsible for? Well, if you're a parent, you're going to distribute the tokens. Child queues, on the other hand, consume bandwidth and spend tokens. I'm going to start using tokens and bandwidth interchangeably, because bandwidth can't pass without a token. So think of them as being interchangeable. Even though they are different things, they work together. So on a parent queue, the priority is ignored. And on a child queue, the priority dictates the order in which remaining tokens or bandwidth is given. The parent is first going to try to satisfy the child's queue's limit at value, which is their guaranteed bandwidth, and then it's going to try to reach the child's max limit if there's any bandwidth left over. This happens in priority order. I'll show you that in a second. So on the child queue, obviously, priority dictates the order in which remaining tokens are given. What's going on? And we have 8 priorities in MikroTik and Linux, because it's based on Linux. 8 is the lowest priority, and 1 is the highest. And prioritization will only work if limits are specified. I can't say that enough. Now we're going to talk about are limit at and max limit values. These are the rules. If you follow these rules, things will be very predictable. If you don't follow these rules, things become unpredictable, and you're going to have a hard time with your queues. So the bandwidth distribution with HTB is the sum. Here's the rule for setting the limit at values. Here's our limit at values. It's in the red. The sum of the child's limit, or all children's limit at values, should not exceed the parent's max limit value. The child's max limit should not exceed the parent's max limit. So don't exceed the parent's max limit in any case. Over here you see we have our child queues, and you add these up and they equal 80 meg, all right? And that's the guaranteed bandwidth, no matter what. Child's gonna get this. If you do the math right, which is very simple, you will always be able to feed your children this much bandwidth. Now the max limit is obviously how far they could go up to, and that's where priorities start to come into play. So again, I'm going to say the rule. The parent will satisfy the children's limit at values first, then any remaining bandwidth is distributed by priority to satisfy the child's max limit values. By the way, I think now might be a good time to just say that the queue colors in Winbox, you see they're all green. The queue color of green means that you have utilized between 0 and 50% of the max limit bandwidth. 51 to 75, it turns yellow. 76 to 100, it turns red. And remember, once you exceed the max limit, or try to exceed the max limit, packets will either be queued or dropped. If they're queued, they're delayed. So now we've seen this on the MikroTik wiki, but we're going to talk about how bandwidth is actually distributed. So first thing we do is we check to make sure that the max limits of all the child queues do not exceed the parent's max limit. That's important. Second, the sum of the child queues limit ats do not exceed the parent's max limit. So we did that over here. We saw that the max limit of the parent is 10 megs. All right, all children are set to 10 megs max limit. Our limit ats are set to 2 megs, does not exceed the parent. Over here we have a limit at of 2, and that's 4. So the math adds up. Everything here is right. This will be very predictable when bandwidth gets maxed out. So let's talk about when bandwidth gets maxed out. The child limit at will be satisfied first. So we have 3 children down here. Each of them are guaranteed 2 megs. So 2 megs times 3 children is 6 megs. Now we have a 10 meg max limit. So 10 meg minus 6 megs that have already been guaranteed leaves us with 4 megs to distribute by priority. All right. So Q4 over here has a priority of 1. That's the highest priority. So Q4 will get the remaining bandwidth. So Q4 is going to get 6 megs total. And that's how that works. Now let's talk about buckets. Here's where the fun stuff happens. Buckets. What the hell are buckets? When I first saw that, I was like, I have no idea what this is about. But now, after version 6.35, you actually have a option to change the bucket. So why would you want to change the bucket? Before, the bucket sizes were hard-coded in the background to 0.1, 10% of your max limit. So let's talk about buckets. And I don't like Deep Space Nine, but this is the only reference to a bucket that I could find. And by the way, that's what happens when you take too much Botox. All right, so buckets. What is a bucket? The bucket's only purpose is to facilitate bursting. Remember that. That is its only purpose. Bursting is when traffic is allowed to exceed the max limit for a limited amount of transfer time. That drove me nuts for a little while. Up until learning this, I was like, how could you exceed the max limit? Well, you can with a bucket. And I'll explain that. So when traffic flow is less than the max limit, the bucket for that queue will start to fill with tokens. And a full bucket will allow bursting at an unrestricted speed until the bucket is empty. All right? And remember, buckets filled with tokens. Tokens is what allows queues to dequeue. If there is no token, packets start to queue up. When tokens or bandwidth becomes available, now tokens will be able to dequeue queues, packets from a queue. So let's see. If a child queue requests bandwidth from a parent queue who has a full bucket, the parent will release all tokens at once, allowing the child to burst. All right? It just dumps them all at once, if possible. Now next, let's talk about bucket capacity. So how many tokens can a bucket hold? Or we really measure this in megabits. So queues are configured with buckets that hold tokens. Well, how many? It's calculated easily. The max limit times the bucket size gives you the bucket capacity. Bucket capacity dictates data transfer. Please remember that. It's about how much data can you transfer. That's what it is talking about. Not flow, not bandwidth, data transfer. And just remember that all children are limited to the parent's token supply. So in the first lab, I'm going to demonstrate a full bucket burst from a queue without any children. Just a single one. Here's the lab setup. We have our NAS drive, we have a MikroTik, and we have the PC here that I'm using. We have a 1 gigabit link that goes into Ethernet 1 to the MikroTik. Ethernet 5 goes to the PC, and we're going to download a file in FTP. Here are the parameters. Max limit is 10 megabits per second. Bucket size is 10. That's going to give us 100 megabits of data transfer. Okay? Data transfer. What's wrong with this? What's wrong with this? There you go. Good. We have some Trek fans. That's Lore. His evil twin, for those of you who don't know. Hey, you just missed the Lore joke, Justin. Lore, forget you. Anyway, so here's the lab set up. What we're going to do is, for the simple queue, under the General tab, I'm going to make the target Ether 5. That's the interface that's facing my laptop, right? And the max limit is only 10 megs. That's kind of small, but check this out. Under advanced, I get to say I'm giving it the maximum bucket size of 10. All right, that's the highest you could go. So 10 times 10 is 100 megabit of data transfer. Data transfer, not bandwidth. Remember that. So over here, once I start the data transfer, you see the first second, all right, in this graph, the bucket completely empties itself, and you get 100 megabits of transfer almost instantly. Then after that, we're limited, we get restricted, and we go back down to our 10 megabit max limit. All right, so I just decided to do a little accounting here because I just wanted to see if what I was calculating is actually what's happening. And so if you want later on, we could talk about this, but you have to reduce all of your traffic to the bit level. So 268 megabyte file is whatever that number is in bits. And then the bucket size is that in bits. Then we take that minus the bucket size gives us that. So that's what we're going to transfer after the burst. The burst divided by 10 megabits per second is that, which is 204.4 seconds. After doing the math, it comes out to 3 minutes 26 seconds for the total transfer. That's what I got on paper. In actuality, I got 210 seconds, which is 3 minute 30 second. Not bad. 4 second, deviation. And down here is the actual file transfer. It said exactly how many bits it transferred in 210 seconds. We're going to do that live. You guys want to see that live? All right, cool. So let me set this up. So I decided to do it with FTP just because it's kind of easy. I was so terrified before I did this. I'm like, I have to clear my browser cache just in case I need to open a window. So let's connect to the NAS. We're connected. Oh, wait. I'm going to start the transfer on this window. And let's open the MikroTik. What's happening? Where's my mouse? Where's traffic control? We're on slide 128. Hold on. There we go. Okay, so let's go to a MikroTik. Pass through. 1 second. Oh man, Nick, I have that Roman problem again. I can't log into the MikroTik. I have to clear everything. Not getting in with the IP. There is a bug with MikroTik and router and Winbox. What did I have to do to fix that? Yeah, I have to delete all the. Yeah. I have to move session. Okay. Oh. Okay. And then we'll log into the tick. All right. Yay. Okay. So here's a single here's a single bucket. I'm going to enable it. And this is with a 10 megabit upload, FTP. Again, the bucket size was 10. So let's go to the, let's see. No, that is a, here. Let's go to traffic. Okay, now let's start the transfer. And once the transfer starts, you will see, oh man, this is getting fun. I'm going to start the transfer here. And you'll see a spike happen. There's our spike. And then we're limited down to 10 megabit. So once again, the spike, obviously, it took a little bit more time to empty the bucket than I thought. But now we go down to 10 megabit. So that's pretty simple. That's in a very simple setup. So let me cancel this. Now let's go back to the presentation. What was I up to? 128. Hold on. Okay, so pretty much what we saw there is what happened in reality, almost. And the second lab is going to be a little bit more intricate. I'm going to demonstrate a burst from a child queue with a large bucket and its parent that has a very small bucket. So what exactly will happen there? We're going to see a ceiling. By the way, I decided to make a flowchart. I was not able to find a flowchart anywhere on the internet about how token bucket bursting happens. So what we saw in the last one was we started to make a transfer. So packets enter here into the bucket. Are there excess tokens in the bucket? Can we burst? That's what that means. If no, then you're limited just to max limit. You haven't bursted. If yes, is there a parent? If there's a parent, well, let's say if there's a parent no, then dump tokens and you go out exit interface. But if there is a parent, are there excess tokens in the parent's bucket? If there's not, you're limited to the parent's max limit. That's important for the next demonstration. If the parent doesn't have a full bucket or its bucket is way too small, you're going to be limited to, let's say, max limit. And if the parent does have a bucket and it does have a lot of tokens, you'll be able to burst. It dumps its token out the exit interface. Here's a good time to mention this. You don't want to set a high bucket size or any bucket size on your exit interface if your exit interface has a fixed amount of bandwidth. Because what will end up happening is you're going to burst out of your exit interface, which your exit interface will be able to, let's say it's a gigabit port speed. You'll be able to send out traffic up to a gigabit, but then your CPE device is going to drop out anything over whatever your bandwidth is provisioned for from the ISP. So be careful with that. So now let's go back to the lab. Lab is going to be child has 10 megabits with a huge bucket like we saw before, but this time we're giving it a parent. And the parent is only going to allow 20 megabit of transfer. The bucket size is very small, so it's going to have a very small burst. So what is going to happen in that case? In that case, when you start the transfer, remember, the best way to describe token bucket bursting is data transfer. How much data will it transfer at its maximum possible speed, right? Now, because the parent is only limiting it to 20 megabit, we go 100 megabits of data transfer at 20 megabit per second. So in about 5 seconds, it's a little longer because the bucket's refilling as time goes on. So let's say it's a little over 5 seconds. And then we're limited, we go back down to 10 megabits per second. So I was supposed to explain all that. But child queue has a full bucket, the parent has an empty bucket. Child bucket is set to burst at 100 megabit of data transfer, but is limited to the parent's max limit of 20 megabit per second. After 100 megabit of data has transferred and the transfer is completed, data transfer returns to non-bursting limit of child's max limit. That's exactly what happens here. So let's show you that in real time. So where do I go? Are we back here? Perfect. We're back here. Let me go and enable. Whoops. Let's enable. Let me put this down. Hang on. right, there we go. So that's set up, and we're looking at traffic. Now let's start the transfer. Where the hell's my mouse? Okay, I'm going to transfer the same exact file, 268 megabyte, but you're going to see how the parent limits the child to only 20 megabit per second for about 5-6 seconds, a little longer actually. And then after that, we're going to drop down to 10 megabit per second. So you see how the hierarchy is always in effect. The children always depend on the parents. The parents distribute the tokens, the parents distribute the bandwidth. The bursting happened, and now we're back down to our max limit. So that's what happens there. So let me get rid of that and continue with the presentation. Now, by the way, there's two ways to burst. There's bursting like this with token buckets, and then there's, of course, bursting with time. I am not going to show the time one now. That one's very simple. Hold on. That one's pretty simple, and I think we have to fast forward. So again, just to show this, because I'm very proud of this flowchart I made last night. The packets go into the buckets, right? Hit the buckets or hit the queues. Is there excess tokens in the bucket? Yes. Is there a parent? Yes. Does she have excess tokens? No. We go to max limit. So we got limited at the max limit, even though the child is trying to burst or is bursting, but can only be fed at the parent's max limit because the parent's max limit, I'm sorry, because the parent's bucket doesn't have any tokens, let's say. So I hope this ends up on the MikroTik wiki. That'll do wonders for my ego. For what? The questions are at the end. Hold on. And I forgot to mention there's the exit interface. But so that pretty much concludes the presentation. Some of the things we learned about, again, was mangling, what it does, how to do it, queuing, what happens in a queue, what happens with queue types. We have simple queues versus queue trees. I hope now you understand the difference. We talked about policing versus scheduling, and we talked about the hierarchical token bucket, the MikroTik Sasquatch, and bursting with tokens. So thank you so much for listening. I hope you learned something. And are there any questions?
Thank you. Yes?
I'll get to your question in a second.
Okay. Yeah, I'm still trying to wrap my mind around when to use a queue tree versus the simple queues. Just because, well, for one thing, the simple queues, they can be simpler, but it seems like they also have almost all of the options that the hierarchical token bucket has. And I've also got some questions about the performance of one versus the other one. For instance, yeah, you have to process rules sequentially for a simple queue, but don't you also have to do that when you're mangling? Because the mangle has the rules in it as well that you have to go through to get into the token bucket.
Yeah, that's right. That is right. So I heard a few questions in there. First one is which one to use. That's going to depend on your setup. Again, how much throughput you're using, what your processors are doing. And the second question was about, what again? Which one was it? You asked about, which one? Oh, that's right. Yeah, well, you would have to look at the packet flow diagram and see which one happens where, because you could use a pre-route, you could use a forward, you could use a post-route. But that all happens prior pretty much to the queuing, right? Has to happen before. You got to classify your traffic before it gets into queues. So look at the packet flow diagram and decide which one's really the best for your scenario. I like pre-routing. It's just because when a packet enters an interface, let's think of it that way. Yanis likes the forward. Post-routing, I only use that if I have to remark something with a related connection. But if you want, I could show you like the details of my Mangle setup like later. Cool. Your question, wait, you had a question about which character would be responsible for a hierarchy? I don't know. Oh, okay. I thought you had a good answer for me. All right, sure.
It's Quark, rules of acquisition.
The Ferengi?
Yes.
I guess you could, but they're more about stealing than. This has order. This is in order. Ferengi are like anarchists. That's true. Latinum bars.
Okay. In a MikroTik router, can we take advantage of hybrid of queues? Say using simple queues for graphing and maximum of a particular address, yet using HTB queues for quality of service. In other words, prioritizing certain kinds of packets by marking them.
I think you just, the question was, what I heard was, what again? Not that I've seen. What'll happen is, yeah, if you use simple queues and queue trees, the simple queues is going to take the traffic first. Unless there's some clever setup that I'm not aware of that can happen.
Okay, thank you. If you have any more questions, you can ask David in the break.
Thank you very
David.
much.